Okay. All right, I think we can start. Yep. Yeah, it's fine. Mhm. Okay, thank you for coming today. Yeah, welcome to our time series colloquium. Yep. Today I'm gonna present about graph neural solver for power grid congestion management, which is my part of my PhD project. Here is today's agenda. First, I want to introduce about the project Grid Assist where I'm in, and the background and motivation of machine learning based grid assist system. And we're gonna have a look on power flow equations. What is DC and AC? What is power? What is voltage, current, impedance, these kind of things. And have a look on solving nonlinear load flow equations with Newton Raphson. And then next, we're gonna see graph neural solver, which have the same objective with Newton Raphson, so nonlinear equations. And then I'm gonna talk about how can I do my derivation and future works. All right. So the project Grid Assist, this consortium, there are companies like Siemens and LEW, which is called Lechwerke. This is a transmission system operator. This kind of TSOs are in Germany. There are 9 TSOs in the entire Germany, and they are managing the transmitting the electricity to city, sometimes country to country. And also we collaborating with Stadtwerke and OPAR-RT, which is a real-time simulation company, and also Avitya Aachen University and FAU. So there are like 35 people in total. And especially in FAU, we are collaborating with the chair of EES, which is Electrical Energy System. And she is the leader of this sub-project. And this last March, we had a consortium meeting at Siemens campus. And last April, we visited LEW in Augsburg, which is transmission system operator, to see their operation system, just like this. They are like staying 24/7 hours and manage all electricity transmission in that Augsburg region. So this is quite confidential operation system that nobody can easily see these kind of things. And we also have team dinners like this. You can see Julian and I. Also Timon is here. And we are also enjoying team gathering like this. All right, so okay, let's see about the background and motivation of machine learning based grid assist system. So it's easy to take the electricity for granted, but the modern life is something not easily imagined without the electricity. So to keep it going, we need a more efficient way to manage the electricity. So electrical grid consists of these 3 main processes: first, generation and transmission and distribution. So we generate the energy from the power plant and transmit the electricity through the substations and the distribution of electricity to households and businesses. And running power grid is getting tougher these days, and it's all kind of complicated things happening at once. We got more renewable energies like solar and wind, and this output depends on the weather. So if the weather is good, we get more energy. So it's always something going up and down. So there are also new demands like especially electrical cars. And this can be plugged in different region and different time. So it also occurs some uneven distribution of the grid. And to top of it, and also the electrical market are more flexible than ever. And power plants nowadays can constantly adjusting how much they produce, sometimes within minutes, and this makes the grid much dynamic. Also, the balancing the grid is becoming too complex for a human alone. So the thing is, we need some smart tools and some automation for faster and reliable decision. Okay, so in the project Grid Assist, the tasks are divided into 6 sub-projects, and Simi and I mainly working for TP5 and TP3. So TP5 is basically building a knowledge database from heterogeneous source of power grid data, and based on this TP5, we developed some automated congestion and fault and restoration management based on machine learning. So today, we will just have a look on congestion management. There are types of congestion. First, the market congestion, and physical congestions, and structure congestion. So today we just focus on physical congestion. And to prevent this physical congestion, the grid should not violate the voltage band, and also should not be overloaded current in the lines. So let's have a look on related work, especially for power grid and power flow equations. So first of all, there are DC and AC. So DC is direct current and AC is alternating current. For direct current, there is no voltage direction change. And for AC, there are back and forth of voltage and current. So as you can see here, in AC, so this blue graph is the voltage, and the red and yellow graph is the current. So if and then the yellow graph is something there is out of sync with voltage and current. So we represent this as a phi, the phase shift. Yep. And so the power itself in the DC is quite simple. So according to the Ohm's law, it is just P equal V times I. So power is usually we are familiar with the watts in the verb, and this is power. And voltage is V and current is I. So in DC, because there is no back and forth, this phase shift and magnitude shift in voltage and current, we can just simply represent like this. But how about power in alternating currents? So it is not that simple to represent. So there are 2 types of power in alternating current. So let's think about we are pushing a box, and then we have power, and once we push the box, and this power directly affect to the moving of the boxes. So which directly used in the actual work of moving, this is active power. But we also need something like maintaining our body and maintaining like the body and the motion of our movement. So once we put like this, and then this is moving, right? And this power is active power, and then something I'm having, but it's just bouncing around my body for the motion. This is called reactive power. But reactive power is not directly used for the movement, but it's important to maintain my motion and my body. So this is the concept of active and reactive power. And so first, we just so since this is somehow alternating for the voltage and current, we just consider the average of it. So we just get this root mean square, and then we represent P as V root mean square and I root mean square. So I max is the maximum voltage. The V max is the maximum voltage, and I max is the maximum current of that. And we just get the root mean square of this, and this is the active power in AC. But we also have some situation that there is a phase shift phi. In this case, we just consider this out of sync using cosine theta. Why? So let's think about the cosine 0 is 1. So there is no phase shift. So this is going to be just 1. So we don't have any loss of power. And every power I'm pushing the boxes is just effect on the moving of the box. Okay. So we represent the active power as V RMS times I RMS cosine phi. So here phi is the phase difference of voltage and the current. And what is reactive power? Reactive power is like with sine theta, it's just V times I sine theta. So sine 0 is 0. And then if there is no phase shift, and we don't have much loss of the power, but it becomes like phi itself, and it's going to be 0. So let's summarize. So active power is the energy in actual work, and the reactive power is energy bouncing around. So in alternating current, we consider these two types of power, and we just combine these two types of power with P plus JQ. So the P is the real part of the equation, and Q is the imaginary part of the equation. So we call it apparent power. Okay. And here is something interesting mathematics for apparent power S. So we can apply Euler's formula derived by Taylor expansion. So here you can see e to the j theta is cosine theta plus j sine theta. And yeah, this P is Vi cosine phi, and Q is Vi sine phi. And then it finally represents as like Vi, which is the Vi star. The star means the complex conjugate of I, which means complex conjugate is just, here we have cosine theta plus j sine theta. Complex conjugate is cosine theta minus j sine theta. All right. So, and we also need to know about what is impedance. So in DC, we have resistance. So you might be familiar with that. But like the active power and reactive power in AC, we also consider one another things, which is reactance. So reactance also for something about direction. So we have this resistance in AC. Also, we have this reactance, and then we combine it as a complex form. This is real part and imaginary part. And this jet we call impedance. And so we also consider the Y, 1 over jet is we call admittance. And admittance is also consists of the real part and imaginary part, and real part is conductance, and imaginary part is susceptance. So the admittance is how the flow, the electrical flow is easily going, and the resistance is how they hesitate by this somehow the preventing power of the electricity. It depends on the line. All right, so these are some fundamental things, fundamental variables in the electricity and power flow. And now we can have a look on the 3-bus system, the 3-bus example. So using Newton-Raphson. And Newton-Raphson is basically to solve a nonlinear equation. So we have a couple of nonlinear equation, and we want to solve this using Newton-Raphson. So Newton-Raphson is already mentioned in the pattern recursion lecture, but this is for maximizing the log likelihood. So for this example, we're gonna use to solve a nonlinear equation instead of log likelihood. Okay. So this is the 3-bus grid example. So we have 3 buses, and the buses are just basically the nodes in the graph. And we have 3 nodes, and each node has the type. The first one is slave, which for the balancing, and then the second bus is PQ. We call it load. This is for consumption, and then the third one is for generating. So we, like the plant, we generate the electricity. And each line has their own impedance. So do you remember impedance is reactance, and like resistance plus reactance. So each line has their own property. But for simplicity, we just remove the we just put the resistance as 0 here. And these are the example. And so our goal is congestion management. So congestion management is we want to prevent the voltage violation. So it is important to calculate the voltage magnitude and the angle of the voltage. So what is angle here? So as we have already seen at the sine graph, so if there is a phase shift and in the sine graph, we have the angle. This is just basically the angle of the voltage. So we have like a slate. In the slate, we already know voltage and angle. But in the load bus, we don't know the voltage and angle, but we just know the P and Q, which is active and reactive power. And in PV, the generator, we know P and V, but we don't know like the angle itself. So what our objective was to find the voltage and angle. So we need to know about these 3 parts: V, the delta, and the V2 and delta 2 and delta 3. So here we have 3 missing variables. So let's formulate like this. So we have unknown state delta 2, delta 3, and V2, and known state delta 1, V1, V3. And yeah, corresponding on this nonlinear equation derived from Kirchhoff's law, we can calculate P and Q, which is reactive and active power, with these equations. So we have like 3 unknown states and 3 like values from P and Q, P2 and P3 and Q. So we have like 3 equations from these like physics equation. And then we have 3 unknown variables with this load and the generator. All right. So, so if you see the formula P and Q, so P is Y times V. So this Y is the admittance. So it's 1 over, so Y is admittance, and this is, the 1 over resistance, 1 over impedance. So this is how easily the electricity flow. So this is Y. So we need to build the Y-bus matrix. And the Y-bus matrix is just 1 over impedance. So we define the impedance like this here. And then we got this admittance like this. And so we can build the Y-bus matrix like this. And so here bus 1 and 2 is J10. For the non-diagonal part, we just ignore the negative sign. And then from 1 to 3, we have J4. And so for Y11, we just add these 2 things, and going to be minus j for t. And what are we going to do is divide it to two parts. So it is magnitude plus zeta. So the magnitude of YB is 14, 10, 4, like this. And the theta, the angle, is phi over 2. And we can represent it like this. All right. And then we have three functions, P2, P3, Q2. And then we want to make these functions equal 0. Since so this is just we got P2 and then just plug into the formula and we got these formulas, and then because we already know the value P2, we can put FP2 equals 0 is like this. And then we want to also calculate for P3 and Q2. And finally, we can iteratively find the unknown variables using Jacobian matrix. So Jacobian matrix is just the combination of every partial derivatives. So we can calculate the partial derivatives according to these formulas. And finally, we can iteratively converge the unknown state delta 2 and delta 3 and V2 using this iteratively converging Newton-Raphson method. And first, we just initialize the value of delta 2, delta 3, and V2, and just using the Jacobian matrix, which is partial derivative of each functions, and we can solve the unknown state of delta 2, delta 3, and V2. Right? Yep. So this Newton-Raphson is basically derived from the Taylor expansion. So we just take the first order Taylor expansion for the Newton-Raphson, and we want to make this fx plus delta x equals 0. And then, using this first order Taylor truncation, we can iteratively reach to the unknown state of the variables. All right. So, and now we have had a look onto how Newton-Raphson works on the power flow 3-bus system. And now we want to have a look on graph neural solver for power system. So the Newton-Raphson for load flow computation is slow. To fulfill this increasing usage, it is important to be accelerated. So we can also consider the fully connected network. This is faster, but just fixed on the same grid size. But graph neural network trained on given size can generalize for the other size. And to simulate a different state of the grid topology size, we just simulate this different state of grid topology and size to generate the train data. And then finally, this paper have proven that this GNN is better than DC approximation, which is just cheap first pass script. And this is also used as a standard benchmark in minimizing feature cases. So here we also have a simple example, which is similar to the previous 3-bus system. We have 3 injections here. This is the plant that generate the energy, and this is the consumer that consumes the energy. But a little bit different, we have one additional line here. So you can see, so we just define these variables, and injection is 3. n lines are 4, and D in is 2, which is P or G, and P and V or P and Q. And the output of this graph neural network should be the current and power of each lines. So we can define the input as like the 3 by 2. So we have 3 injections, and each injection has 2 column, 2 feature vectors. And the output is each line, the rows are each lines, and the columns are the current of the terminal. So in the line we have 2 terminals, the terminal origin and the terminal extremity. So there are I origin, I extremity, and P origin and P extremity. So why do we need this current and power of each line? We just want to figure out the line is overloaded or not. So basically, the graph neural network itself just input the 3 times 2 matrix and get the 4 times 4 matrix as an output, right? Okay, so the graph neural networks works like this, and it has embedding layer and the propagation layer, which pass the messages from the node to the other node, and finally the decoding layer to output the currents that we want to know. So this is the graph structure. So we have 3 adjacency matrices to represent the graph. And first adjacency matrix is a injection matrix. So this injection matrix is represented as like this. We have 4 columns which represent the lines, and 4 rows and 3 columns which represent the injections. And so if you see this A injection, so this -1 means if you see line 1, so line 1 is going into injection 1. So if something is going into injection 1, we put -1. And here 1, 2 is 1, which means line 1 is going out from the injection 2. So you can see the yellow line, the line 1 is going out from the injection 2. Okay? And we use these adjacency matrices. So first, we also use 2 types of embedding layer for productions and consumptions. And because we need to put this into the latent space, and we have different variables for productions and consumptions. So we need a different embedding layers to somehow put into the same latent space, and then it's going to be updated using neural network as the graph neural network. So we use different embedding layer for productions and consumptions. All right. So this is the embedding step. First, we get the 3 by 2 matrix of X, and then this is embedded by the embedding layer, and then multiplied by this adjacency matrix. And finally, we get the matrix like n lines times the embedding dimension. So each rows just represent the lines. So finally, we want to know about the characteristic of each lines. Okay, and then the propagation steps. So we just iteratively update the embedding. So here we have 2 kind of adjacency matrices as well, for the terminal origin and for the terminal extremity. So here we got the first H, the first latent vector of H for the lines. And then we just want to aggregate these two parts of the line information. So the left part is for the neighbors on the origin side. So we have here, this is origin. So it starts from injection 1, 2, and then downstairs. So this is the origin. So this part is to aggregate the neighbors from the origin side. And this is the part that aggregate the neighbors from the extremity side. And then we just iteratively update the embedding of H for each lines, and then until certain convergence criteria. Okay, and then we also add one residual block to make it somehow relaxed and to prevent the loss of information. And this is the entire propagation steps. And this is basically the cheat sheet of every tensor shape that we are input, and then between the embedding layers and the graph neural networks layer, the propagation layer, and then the output of the decoding layer. So the decoding is just one additional neural network after iteratively updating the state H, the state of the lines, and then we finally get the output after the decoding layer. So this is the full architecture of the graph neural network. So first, we have each injections, each buses, and each buses can be consumer and the generator. And consumer has their own variables and like PQ. And the generator has their own variables PV, which is active power and voltage. And each buses has two variables and it represents as X. So we have X1 and X2, X3. And this is multiplied by the adjacency matrix of line. So it's going to be these four rows. So each rows represent the line. And then for the propagation layer, we consider two parts, the neighbors of origin and neighbors of the extremity. So these are divided into two parts and eventually aggregate these two things. And during this iterative updating, we somehow learn how to find the unknown states. And then finally, we can decode the final output we want to have. All right, so this is the methodology, and this is the experiment they have done. First, they test on the same grid size and topology. So the grid size means the same number of nodes. And the topology, the same topology means the same connections between the nodes. And first, this is the same grid size and same topology during both training and testing. So this is exactly the same case with Newton-Raphson. And the second case is we have the same grid size, the same number of nodes, but different topology, the different line connections between the topologies. And the third case is we have also different grid size and topology itself. The topology is the connection between lines. And so we train certain topology and certain grid size, and it can be used for another topology and another grid size. And they basically use the L2 loss as a loss function. And then the target is the company. This is RTE, the company in France. So this is also a TSO, transmission system operator, that interested in this load flow calculation. And this is also essentially based on the Newton-Raphson. And so they just replicate the output of the Newton-Raphson solver of their own system. Okay, and for experimental purpose, they run 20 times of the training and inference because since the neural networks can behave differently each time you train them, and even with the same data. So they just evaluate this with the median and then 20% and 80% percentiles. All right, so another metric they used is MAPE, which is mean absolute percentage error, and this is to check overloss for security. So they just want to see the top 10% score of highest current because their goal is just to figure out which lines are overloading, and this is the metrics for that. And this is the result of the first experiment that has constant power grid topology and constant grid size. And they also compared using fully connected neural network. And as we can see, the proposed graph neural network has the low loss. And then also this MAPE 90 A is also lower than the fully connected neural network. And this is the DC approximation, which is the first basic, first glance capturing for the method for the electricity overload. And definitely the proposed GNS is better than DC approximation. All right, so you might wonder how does fully connected neural network works and what's the difference between this graph neural network? And so the answer is fully connected neural network just is only working on the same size grid and same topology, and it feeds the 3x2 matrix, which is 3 injections and 2 features, and then just directly output the 4x4 matrix, which is the properties, the current and power of the line. So this is just directly output the target without considering the adjacency metrics. But the graph neural network considers 3 adjacency metrics. First, injection. First, between buses and the lines, and second, between lines and the terminal, and the third also between lines and terminal. But first one is for the origin, and the second one is for the extremity. So that is the difference. And finally, the graph neural network that consider the adjacency metrics, which means it plugs in the graph structure into the neural network. And as you can see here, the graph neural networks works better. And here is also the second experiment with random grid topologies of constant size. The number of buses, number of nodes are the same, but the connections are different. So here, also they showed this is better than this approximation. And here, the last experiment is most interesting because it can work on different grid size as well as different connections, different topology. So they just trained on the 30 nodes and then test on the different number of nodes. So they figured out this is somehow working well, even if it just trained on the constant size of the grid, but also working well on the less number of nodes and then the larger number of nodes. But there is also some outlier that at the grid size 100, And the author said it would not be the representative of actual power system, but we need to think about that. All right. So basically, yeah, they used the 30 buses and then 42 line grid. So the edges are 42 and then the nodes are 30. And the experiment C, they trained on 30 bus and these lines, and then tested on the wide range of size of the grid network. Right. So they also test on the computational time and compared to their own Newton-Raphson solver, it is 2 times faster. And there is also some bottlenecks because they implemented it as in the TensorFlow, but the TensorFlow stores the JSON matrix as a dense matrix, and so they suggest this we can somehow improve the introducing the sparsity of the matrix instead of using dense matrix, and yeah, so there are also discussions and conclusions, and they want to improve this great neural network with different methodology. And yeah, and this is basically based on these two predecessor studies, and there are already two comprehensive dissertation I want to follow. So first one is from France, a French university in Paris, and deep statistical solvers and power system application. And the second one is learning on graphs from theory to industrial application in power management, distribution grid. And what I have shown until now is based on this dissertation. And there are also successor graph neural network that improve the architectural things and also their limitations. And I also think about what would be my dissertation. And so basically, you might heard about physics informed graph neural networks. And physics informed graph neural network is like we just it's also introduced in another studies, but at the studies we've gone through this graph neural solver, it just mimic the output of the Newton-Raphson, but in physics informed neural network, they also put it some kind of unsupervised learning, but they directly incorporate the power flow equation itself. Like we have seen the P and Q, how P and Q is defined, and the physics-informed graph neural networks internally run these Newton-Raphson somehow in the graph neural network and directly output the unknown state that we want to know. So we actually don't need the target value from the Newton-Raphson. This is the so next in the next paper, this is well introduced. All right. So actually, my dissertation, I'm thinking about at the end what would be my dissertation. So first, we want to solve these power flow equations, these load flow calculation using like Newton-Raphson or graph neural networks, and we want to optimize it and make it faster. And then finally, we want to manage the congestions and we want to cut the voltage level. And then we want to somehow manage the overloaded current in the lines. And for the decision making, we finally need to use reinforcement learning. And yeah, so I'm still somehow figuring out what exactly I can improve based on these two predecessor studies. And yeah, finally, yeah, I need to somehow improve to support the grid assist system in the Lechwerke and other TSO companies in Germany. All right. So thank you for listening this long presentation. If you have any questions, please feel free to ask. Yep.
Paula. I have a question. So I know, and I also noticed and know that the state of the art is physics for neural networks and graph neural networks. How did they behave in different topologies? So graph neural networks, they are really adaptive. Also, in physics for neural networks depends too much on an equation modeling on certain topology. So have you seen, or do you think that this will be tricky for you because it's really adaptable to only one topology? And correct me if I'm wrong, because it's what I understand.
If I understood correctly, so the physics informed neural network. Mm-hmm. You think physics informed neural network could struggle to adapt in the varying size and varying topology?
This is also a question that I have. What I see is they adapt too much to modeling an equation. Mm-hmm. And then the thing with that is probably certain topologies will have variations on that. Mm-hmm. I'm not sure if you know, or I'm not an expert, so this is what I'm is more intuitive. Yep. Do you think that this will be a problem if you're trying different topologies, or have you seen that they when go to one topology to the other? Because what I saw here is you try different topologies but Newton-Raphson, and then you went to graph and physics, and it was more centering on center of one topology. So do you think that this will be a problem, and maybe you can go into that?
So this problem is already solved in the next two paper. So here, so this is kind of physics informed neural network that does not try to imitate the output of Newton-Raphson, but directly somehow incorporate the physics informed equations in the graph neural network. And then they successfully test on the varying size of grid and topology. But yeah, so I'm also somehow curious how they deal with this everything in the graph neural network. So I'm still reading these papers, and one day I also could present. Yeah. And this is also another paper that used this physics informed neural network. And so they mentioned this because this is physics informed. We don't have the label from the Newton-Raphson, and they consider this as an unsupervised training of GNN. So actually, the concern you had is somehow solved in these two papers.
Okay. Yeah. Okay. Yeah. So kind of define the nodes doing an supervised, or trying to imitate and supervised manner because. Okay.
So they basically use something improved graph neural network structure like this. The simple GNS used just the neural network, simple neural network, not the LSTMs. But here they use LSTM for each node, and they also consider the slack bus here.
It looks like kind of propose a initial random node, and then they kind of adapt the node to better fit it to the program. Okay. Thank you.
Yep.
Can you can you say something about the scalability?
Scalability.
I'm assuming electric grids are really huge. Even when you perform simulations, usually time consuming because you need to take the inverse.
Yep, right, exactly. That's the problem of Newton-Raphson.
Yeah, so with graph neural networks, are there any physical limitations on how big of a network that can be solved? And how does it scale from a small network to a large network?
So according to the paper, it just tested on like from 0 to 100. So it's relatively small so in the real grid we have like 9,000 nodes, and learning on this kind of scale, we definitely need the training data itself with the varying size. But so here also in the successor paper of the GNS, they suggest these four cases from 9 bus and 118 bus. But so the scalability we must consider. So what we are going to do is we have the data from Leschwerke. So we are collaborating with this company, which is a TSI company, and they actually, I already got the data from that, and they have something like 9,000 terminals, and we want to somehow generate the data from this topology and the grid, and then we also want to test the scalability on different size of grid and topology. All right.
Okay. I have just curious about some approaches, especially because you want a topology agnostic model, right? Are there any approaches which break the entire graph into subgraphs and then solve the equation on subgraphs? And because each subgraph is also there is some hierarchy within the graph. Are there any approaches which considers this problem from that viewpoint?
That's exactly what I've seen in this graph.
Okay.
This approach, and they just combine every subgraph into one huge graph, and then train this huge graph using one graph neural network.
Okay.
And then once it is trained on this huge graph, and then it can use for the inference of any size of the graph. So what you mentioned is exactly in this paper.
Yes, it will be a pinpointing question. So actually, will be kind of question for that of you. So what you mean is like something like a general graph that makes one decision and another subgraphs that will split that decision after. Is
Not
what
from-
you wanted to say?
No, not from my perspective. So larger the graph, the more complex it is in terms of the connection. But if we can break down a larger graph into a set of 3 nodes or 4 nodes, the number of possible connections between them is very limited. And then you can use a mask and train different versions of the small graph.
So parallelize
Something.
more than
And
okay,
now
not
this-
make like decisions hierarchically is
Yeah.
more parallelized.
Yeah, and then now this subgraph can anywhere, if you break the bigger graph into subgraphs, the same model can be applied because you have already masked the connections and tried different combinations. And if you go one level up, 2 subgraphs can be considered as 2 nodes in the larger graph. And I don't know if it's possible, but
It's something similar, but moving on hierarchical decisions.
yeah, I don't.
No, but not on like parallel processing. It's also interesting. Yeah, I think it's a really interesting thing because I think they do it all at once. They just define these 100 nodes or so, and then they do it all at once. I think this is super cool idea.
Also, have you thought of minimizing the number of nodes in the electrical grid itself? Like sometimes there are some methods to tell you, okay, this number of nodes can be equivalent to less number of nodes. So instead of having, for example, let's say you have some number of consumers, you can make them like one consumer instead of all of them together. And then you do the simulate, or like when you solve the equations, it can be done easier.
Yeah, that also made much sense. Yeah.
Was it all in the same voltage level in the papers?
You mean like high voltage, medium voltage?
Was it all of the same level, or did they have different levels in the grid?
At the same level. So mostly in medium voltage.
I think if you would have different levels, could do what you're saying.
Yeah,
Because you
also
have like one low voltage grid, you can treat as a single load.
Another point which I was thinking is if you can get probabilities of congestion on different parts of the network, you can also isolate based on that. Maybe a certain part of the network is never congested, then maybe you can simplify the problem.
And then you could like speed it up.
These are just random points in terms
Because the TSOs probably know the critical lines.
Yeah.
And the problem with these things is like they are really nice, but in terms of usage, it's always a problem with memory, always a problem with like computation. And I think if you do it in a more efficient way, it will be really nice work. Very safe.
And it's always on your stainless static time frame, right?
You're asking, right? It's static time point.
Like the problem you're solving is always for a single static time point.
Yeah, so here, as far as I know, the time points are not that important, but definitely the state itself are different, depends on the time point. But here, the congestion management is for the voltage violation and line overloading. So like depends on different states of the buses. It affects to certain buses voltage, and so we can somehow simulate the like voltage violation situation, and also just the normal situation without congestion. But so we also have multiple time points with different state, and this is also could be one another sample to use as a like congestion, the training set.
So the algorithm should be space and time marching, or
Pardon? Space and time.
time mark. So they should. So Newton-Raphson is an iterative solver for an equation for which you don't have a solution. Right?
Yeah, the solution is there, but it is not. We could not directly solve because this is nonlinear and there could be multiple solutions. So that's the reason we use Newton-Raphson. And sometimes there is no solution.
Okay, and this solves at the given state. But
at the given state.
In electricity grid, I'm assuming you also solve for a future time step.
Yeah, in the different state.
Yeah, so there is simulation or calculation is happening for time t plus 1, t plus 2. No?
You treat everything as a single snapshot, right? You're not doing it continuously.
No, like that is also for the given node.
Like for example,
you can create better space marching and time marching.
So like sometimes you have a node that is affected by the nodes around it. Sometimes it's only the node that is upstream of it, like the node that is giving it something. Okay, and so this is like this is one variation, and then the other one is that sometimes it's affected also by its own history, like the node's own history, like if it has some memory. Like it stores some information and it keeps forgetting it after some time. So it's affected by the points around it, and it's also affected by its own history.
It could be like that.
Is that something you have to calculate? No.
No.
So
Yeah, in current situation, it's not like that. So
Like what they would do, they would like simulate, they would disconnect the line, and they have to redo it all again.
Yep.
For a new environment.
okay.
Because that's what changes in it's not time itself,
Yeah.
but it actually changes in the grid, like
Yeah.
turning off generation or adding load.
So it's just natural. Like it's
just snapshot.
Yeah.
That's why it's really slow to solve for like multiple futures.
But he will also work with physics and formula grids.
Yeah.
And like also,
We cool.
So I have one point that I want to share. The idea he was sharing the subgraph, that is very interesting. But I was also reading the paper physics informed solver for this problem. So what I understood that each node itself is learning the physical equations, and it is passing the information using message passing to its immediate neighbors.
Yep.
And maybe neighbors far away from the current node. So they are getting the information through this message passing. So it is kind of if the current node is not directly connected to other node, the node that is far away from it. So the node far away from it is somehow getting the information of the current node. So the idea of the subgraph is kind of implicitly implemented in this scenario, because when we are thinking that we have to if we could use the subset of the smaller graphs and consider it as a single node, but in the solver physics informed solver, so here it is also, I think, implicitly working in the same structure or whatever.
Yeah. So right. Yep. Like since we somehow propagating the state of each node, and it eventually somehow propagating to every connections. Even if it is so far from here this bus to that bus, it's somehow the information is propagating from here to there, and then farther, and then it's less, right? Yeah, makes sense. All right. I have some comments maybe. I mean, in general, do you already have the data to work on your project, or are you still waiting for it? Yep, I have the data. I have it. And you already have a plan, like what you want to do next? Because, I mean, you will probably talk about it with Simin, or you guys will organize something, I don't know. But since ICAS is the next conference that will happen, I think it's a good idea if you have a plan for a paper, at least for that, and start from there. But I guess you guys talk about that. Yep. Actually, we already have the data. And here is the data actually from LEW-Werke, the transmission system operator. And it's quite complicated, and so Timon is now in the meeting, the chair of EES, and he already gave me the data, not from this Werke data, but for a toy example of just to try train the graph neural network. And plan is first, we want to try with the toy example with like 5-bus system. And then this is the data I got from the Werke. So here, so it also takes some time to understand what these objects are what are these objects and what does it mean? And we have like connective node and 3000 and terminus extremity and origin of the line. So it has 10K, and we are somehow investigating its links. And yep, you mean once I have the data, and then we could try.
Yeah, maybe I mean, for instance, starting to train some graph neural network to replicate what you show in the paper with your data, if possible. It's a good idea. It will give you already an idea of what you can propose or include new in your project. So definitely, yeah. For instance, something I have seen lately with graph neural networks is that people include an attention module somewhere. And apparently I guess for your problem makes sense also because of management.
Yep, exactly.
Load management or.
Yep. So yeah, we also can somehow introduce new architecture of graph neural network. Here we just use LSTM here. So I would suggest Karim just substitute this LSTM with XLSTM. And XLSTM is consists of LSTM and XLSTM with memory mixing. So it's going to be more efficient with complex representation of the vector, and also finally going to be faster inference. So for your project, it would be thesis. You also try to do that, and I can also try some attention-based graph neural network or some retentive network based, which was from my master thesis. And for the architecture design, we could try many things. But the most important thing is how can we train on the data of TSO is the Rechtwerke, and it's going to be challenging because the data itself is not easy to understand, and we need some pre-processing to use it. Yeah.
We also look at similar fields where you can borrow concepts and apply for this.
There are a lot of physics solvers, not only for electricity, but as I've read in the paper, there are a lot of solvers that highly computational extensive, like the case of Newton Rhapsody and load flow, and they also need some faster and economic solution. But I don't know the specific domain, but I've just read some part. There is already some physics neural solver, and they need faster solutions, etc.
And because when we were talking, my mind went to I think some people model brain networks.
Brain.
How electric impulses move from neuron to neuron, etc. Maybe, I don't know, there are some works from which we can borrow these concepts. And for the attention thing, I was thinking, if you have an image, you divide it into patches, and then you have patch embedding, you do positional embedding, all those things, right? Maybe the graph also can be patched.
Yeah, for instance. I think that's a nice idea to include. You guys should talk.
I can only fathom at the higher level. You go inside.
That's how you start. Cool. Nice. Okay. Any other comment, question? No? Yes?
All right, from online, there's no question, right?
Okay. So, by the way, what do you guys think? So will be in China for the next 2 weeks, so I cannot attend the colloquium very likely. Either, I mean, you can continue, of course, and someone takes care of the colloquiums, or we see each other again on the 12th of June.
Do you know already what the plan is?
For
Timetable. There's a timetable.
That's attack is till next week.
exactly, so he can either present his stuff.
Is he online?
No, I don't think so.
Yeah.
Okay, so I let him know then that he will prepare something.
Paula here.
Paula will be also in China.
Okay.
So yeah, and after that, there is no, I don't think, no, there is no.
No, next week is holiday.
It's holiday.
Yeah.
Okay, so on the 29th is the next one.
Yes.
Yeah, okay, he will present the stuff. All right, then it's fine, whatever, it's okay.
Maybe you can do it on the 5th. In 2 weeks. Because in 1 week is holiday.
Yeah. And the next,
In 2 weeks we don't have anything.
what we have from, okay, so we can move it for the next one, no?
No, the 12th you guys will be back, right?
5, yeah, you're right. Okay, yeah, so we move it to the 5th of June. Okay,
I think it's important. I think it would be nice if you can comment on this PhD topic in the plan, because as group leader.
That's what I'm saying. I mean, I don't know how is the connectivity, let's say.
I can ask him. If he can push his talk.
I think you can.
Or we move it, and then I can for sure assist once I'm here again.
Or you translate a single paper from his domain so we get familiar with it. And then the whole PhD topic.
We can talk to him tomorrow. Later.
Okay, then I plan accordingly. All right. So we see each other on the 12th. All right, so we see in 3 weeks.
He told me that I have to also present my project proposal here.
Yeah.
So if there is any available date next, I can also present.
Do you already have it ready?
No, I don't have it all ready, but I will prepare.
Like in 2 weeks?
I think for 5th of June you already have something.
Yeah, I guess I can prepare.
Okay, then
Okay.
5th
of June. Okay.
Can you put the
Yeah, I
date
will.
on the calendar?
Yeah.
Okay, good.
It's 15 minutes, right?
Yeah, 15 minutes.
Okay.
Nice.
Otherwise, Julian is terrible with the time. Okay, guys, see you next time.
Will you be back for a package, right?
Yeah.
All right, guys.
Okay.
See you.
See you. Thank you for your talk.
Thank you.